morning. My name is Gaetano. So I'm a biomedical engineer. So what I'm here for is to introduce to a topic that sometimes physiologists and neuroscientists they kind of overlook a bit, which is the bioelectromagnetism, which leads to the amplifiers and the filter that are used to record the data that you actually use in your neuroscience and electrophysiology experiment. So every time that you actually deal with signals, even if you don't know, you deal with amplifiers and you deal with bioelectromagnetism. Knowing a little bit of these things and the phenomena behind what you actually record will help you to understand a couple of things. Most importantly, it will make you able to distinguish between signal and noise. There are a bunch of physiological signals which they actually look like noise. And there's a very, very thin boundary between a good recording and a terrible recording. And sometimes a terrible recording is going to lead to false results or misleading your experiments and your direction in your research. In order to do that, I'm going to start a little bit discussing what is an amplifier and what it does. But firstly, let me introduce you with an interesting concept, which is the concept of bioelectromagnetism. What is the bioelectromagnetism? Well, the bioelectromagnetism, as the word suggests, is the electromagnetic fields emanated by sources inside the body. In these examples, they are sources inside the human body, but this applies to every kind of animals or plants or anything that we'd like to record physiological data from. Some of the sources, they are purely bioelectric, if you like. So they work by means of electrical fields. Some other, they can mostly excited by magnetism or magnetic fields, and we actually record the responses. So at the base of all of that, there are some important equations which I'm not going to discuss, which are the Maxwell equation, and they govern everything that is done in electrophysiology and in neuroscience. Believe it or not, the same kind of principle at the base of physiological measurements, they are at the base of biomedical imaging. So even if you do magnetic resonance imaging, sometimes functional magnetic resonance imaging, and all these kind of things, which are useful in particularly in the fields of neuroscience and sometimes in psychology, you're actually using the same equation and the same principle. So one other little remark about that. Sometimes we record signals to solve the so-called inverse problem. What does it mean, an inverse or forward problem? You call it forward problem when you actually have the source and you describe using the Maxwell equation the signal that you're going to obtain. And sometimes this is also called modeling. Maybe you do it when you have the model of a network of cells and you want to understand what is going to be the results in terms of spike trains or things like that. That is an example of forward modeling. Instead, you call it reverse modeling when you actually have only the signal. You have a model of what we call volume conductor, which could be the entire human body, and you want to describe the source starting or the behavior of the source starting from the signal. One example that is pretty easy to understand is interpretation of electrocardiogram. So doctors record electrocardiogram and they try to understand if that cardiovascular system is healthy or not healthy. And from the signal itself, they actually can devise where the problem is within the system and maybe try to fix it. There are some sources down here for the lecture. Couple of them, they are free to download. So, for example, this book down here, the Malvio Plonze Bioelectromagnetism book, is free to download. It's an interesting book to have in your, if you want, library. Although this book starts from the Maxwell equation and applies them to the physiology, it describes the bioelectromagnetism properly, starting from the cell, and also describes how you should record spike trains and all these kind of things, EEG and ECG and all the major signals. So it's an interesting book to have, and it's free. The medical instrumentation application and design, you can actually download it through the library of Western Sydney University. I'll probably Yossi, this projector is terrible. Let me see if I made it worse. Okay, not possible.
It's okay, we're gonna say that.
Yeah, but it's. Okay, before I break it completely, let's leave it like this. So probably Yossi has discussed these things pretty extensively. So what I'm not going to going back to what Yossi have told you, but I'm just going to probably discuss these things a little bit in terms of bioelectromagnetism. So if you like, you can talk about bioelectromagnetism as the results of the electrochemical activity of a bunch of cells, which you know now they're called excitable cells. So those are the fundamental components of nervous, muscular, and glandular tissue, and they obviously work by means of resting potential and action potential. So probably Yossi has not told you that there is a peculiar subclass of those excitable cells that they're never at rest. So they actually produce continuously action potential. Can you guess where they are? They are inside the heart. So the basic sinusal rhythm inside the heart is generated by this subclass of cells, which they never sit at rest. The way that the membrane potential works, obviously, as Yossi has told you, it depends on the imbalance between ions inside and outside of the cell, which is regulated by the aperture and closure of some specific ion conduction channels that they allow some of those ions to get displaced from inside to outside of the cell and vice versa. So obviously the action potential is the mechanism that is seen when you measure the voltage across the cellular membrane to rebalance the flow of ions between inside and outside of the cell. From the electromagnetical point of view, these things actually can be seen as a circuit. So the way that you see these things as a circuit, you actually represent the membrane as a big capacitor, and you represent the channels as a controlled, if you want, current generator, or controlled impedance in series with a voltage generator, where the voltage over there are just the known alpha cell potentials of the ions in question, which they are sodium, calcium, and chloride. I expect that Yossi has done a pretty good, extensive few lectures on the action potential. Obviously, I'm not going to rehearse those things. I just have found, and normally when I discuss these things with my students, which they not always are physiologists, this recap over there on YouTube is a pretty interesting recap of the action potential. So I told you to leave it there in case it's needed. One thing I want to stress out is the existence of the refractory periods. So cells, they cannot spike, if you like, again, or generate a new action potential into the absolute refractory period, no matter what. And if you poke hard enough during the relative refractory period, you can actually elicit another action potential from the cell. So that is important to understand that, particularly when you get to stimulation. There are some stimulation that if they are not timed properly and you stimulate into the refractory period, it may be that you actually inflict some damage to other tissues trying to force the stimulation. And that's one example, the cardiac defibrillator. So there is a reason why the cardiac defibrillator, they never charge it too much, they start low. And secondly, the cardiac defibrillator normally has an ECG signal amplifier inside that try to detect if there is a residual rhythm, particularly if there is a P wave. Because what it try to do, it try not to shock the atria if the system has a functioning atria. So all these kind of things, if you design experiments that they include stimulation, they need stimulation, you might want to take into account the specific refractory period of the tissue you are going to act on. Sometimes it's just difficult in case of the brain, but for muscular and nerve stimulation, this is easy to take into account. So I mentioned to you that there are some specific cells which they actually don't need any stimulation to produce an action potential. Those cells, they are inside the heart, only inside the heart, and they are the cause of specific diseases when they are defective. The diseases are called arrhythmias, so there's more than one kind of cardiac arrhythmia. So this is the full kind of chain of activation of the heart or generation of the ECG. So each specific activation following. So the heart rhythm is generated by the sinoatrial node, which sits up here. And that's why the normal heart rhythm is called a normal sinusal rhythm. Those cells, as you can see, if you recall what Yossi showed you of all the waveform of action potential, you see that this one is represented with something that has like a down overshoot, and then it goes up again. That is because this cell, the membrane is never resting and can actually generate a new action potential as soon that this goes up again. So these cells, they are designed to beat between 50 and 80 beats per minute. That means that a heart left to its own, according to the genetics and the random cases that formed each one of us, the heart is going to reach a kind of a steady rhythm that goes and beats according to the sinusal node. So I'm not going to delve into the mechanisms that propagates the heartbeat, but basically the atria will beat with responding to the sinus node. The beating of the atria is going to form some specific action potential that then is collected by another particular subclass of pacemaker cells, which they are designed to beat a bit slower than the sinoatrial node. That is because Mother Nature accounts for failure. If something happened to the sinoatrial node, that means that the heartbeat is not generated anymore from the top of the atria, so the atria potentially are frozen. They never beat, but the ventricle is still beating. and they start to beat with oops, to a speed that is proper of the atrioventricular node. The atrioventricular node is the only part inside the heart where there are nerves connected, which are designed to spread the beat to every single cell into the myocardial of the ventricle. That is because you want a synchronized contraction. So probably Yossi have introduced you to the concept of motor action units into muscles. Has it? Not yet? Okay, so I'm gonna do it then. But anyway, the way that muscles, just as anticipation, the way that muscles they contract is because one motor neuron is going to spread the contraction stimuli to some specific cell. So the smallest amount of force that you can exercise with any given voluntary muscle depends on how many muscular cells they are innervated by one single motor neuron. So mostly muscles, they are divided in a number of even fiber, and each of those fibers, well, not each, a group of fibers, they are controlled by a single motor neuron. So if you want to exercise maximum strength, all the motor units, they try to contract almost simultaneously. They can't, because depends if you want to sustain the maximum strength or not, because sustained contraction is achieved by rhythmic contraction of different motor units. But in any case, for the heart, because you want to exercise maximum strength at well-defined timing, almost every cell is reached by a piece of nerve, so that they are activated almost simultaneously. So one little thing still about this figure over here. You see all those graphs, and you're probably going to see plenty of those recordings, that they are a basic action potential, and you're probably going to record a few of them by yourself. Recording or deciding how to do the recording of those signals is important, and that's the concept of the volume conductor. So these figures over here represents a number of different volume conductor for the same experiment. So what is the experiment? You have a piece of excised nerve into saline bath, and you can apply stimulation, and you have some recording electrodes to it. So obviously the most trivial example of volume conductor is represented from this mouse today is overly sensitive. Is represented by this graph over here, which you actually have one stimulation electrode and one recording electrode, and they are into the same saline bath. So if you change this thing, for example, if you make the stimulation remote, so that you're actually not stimulating anymore one single cell, because you're not impaling the same cell, but you are a bit up onto the nerve, so you're actually stimulating a group of cells. What you record is a compound action potential, right? And that is the graph you see in B. But this is in an excised, still is a kind of a trivial volume conductor. You can easily see it and define it. And you probably will understand what is the volume conductor definition just looking at the graph once you've seen them enough. Obviously, things get more complicated if you try to repeat these experiments in vivo. And that's the last graph at the bottom in C, where you probably can still see the action potential, but obviously the amplitude and the timing of the action potential with compared with the stimuli depends from a number of other things, because it's a fully alive network, so there's lots of other processing going on onto the nerve and into the body. So the complexity of the experiment and the complexity of the data change according to the definition of the volume conductor. Often physiologists, particularly electrophysiologists, they make an interesting assumption. They say, okay, let's imagine that the human body is a sphere. And that is the most kind of trivial volume conductor applied to the human body as possible. Believe it or not, this applies for recording like EEG, ECG, or EMG, so electroencephalography, cardiography, and electromyography. So the concept of volume conductor completes the concept I gave you at the beginning of the forward and inverse problem, because now you can see what sits in between, what is the model that you need to use to actually understand what you're doing. And as I said, you could do some forward problem, so you have a source, like cells into a neural network, and you have your volume conductor, which could be, okay, if they are excited cells, so they sit into a slide or they sit into a saline solution bath, then you can sketch some equation and you can foresee, you can understand what's the signal you're going to obtain when you perform stimulation. Reversely, you just have the signal, then you know, or you can make hypotheses about the model, and you describe the behavior of the source. Again, in the same example I gave you, and then the example that is here on the slide, you record the signal like the electrocardiogram, you make hypotheses on the volume conductor, and then you try to describe the behavior of the source, in this case the heart. And obviously things get interesting when there's some unforeseen signal that you try to link to disease or disturbances. As I said, there are some trivial and non-trivial volume conductor which you need to get a bit familiar with. So obviously the most used one is the one that is underlined over here, which is a finite homogeneous. That means we have a well-defined shape which is spherical, and it is an homogeneous. That means the inside of this model is all the same, and is a conductor. Obviously there are some other, which they are the infinite and homogeneous, or the finite and inhomogeneous. The last one, although is the most realistic one, because everything that we do is in a confined space, so as a finite boundaries, and probably will be inhomogeneous if you think to the same example of the trunk of nerve into a saline solution. Well, you are going to have your Petri dish short container, which has some characteristics. You're going to have the electrodes, which they have some other characteristics. You're going to have the saline solution, which has some electrical characteristics. And you have the actual piece of nerve with all its boundaries and a different kind of tissues and characteristics inside. So although this is the most realistic way of doing the thing, you cannot actually do it unless you're doing some very basic experiments that you can characterize properly your finite and inhomogeneous volume conductor. And that is mostly the case of impaled cells. So if you have cells, isolated cells, that you can actually use individual electrodes on each cell, then you could use the last volume conductor model. These are some examples of realistic experiments that you might gonna face. So those are some of the most used existing models for human tissues, particularly for the chest and the head. So every time that you actually try to do something with EEG, you are applying this particular kind of volume conductor, where the brain is seen as a sphere, inside another sphere, which is the skull, inside another sphere, which is the scalp, and so forth. One point of recommendation is the interface with volume conductors. How do you interface with the physiology, with the cells? You use electrodes. Sometimes you use saline bridges, you use needles, you can use a lot of kind of electrodes. And in case of non-invasive recording on the human body, you just use electrodes. When the electrodes are inside the cell or on the human body, you might want to consider them as a part of your volume conductor, of course. But they add some inhomogeneous to your volume conductor. You might have thinking that is homogeneous. So it's you better off model the electrodes and all, well, not just electrodes, all the interfaces with volume conductor on their own. So in order to clarify how difficult it is to model electrodes, and if you do electrophysiology experiments involving human participants, you're going to place lots and lots of electrodes. This model gives you an idea of how difficult actually it is to take into account the interface between the electrodes, for example, and the skin. So in terms of bioelectromagnetism, we all try to bring everything back to resistance and capacitors or impedances in general, and obviously current and voltage sources. Electrodes, they are mostly metal, and they are put in contact with something like the skin or cellular membrane, which they don't have a neutral pH, right? What does happen if you put a metal in contact with something that has not a neutral pH? Well, you generate a half-cell reaction. You generate either a reduction or an oxidization at the interface with the electrode. And that's the reason why in all the model you have at least one voltage source which represents the half-cell potential of that specific electrode material. There are different electrode materials, and sometimes you put a gel in between, or a conductive paste if you want to glue the electrode in position. For example, if you apply electrodes on the scalp during a recording, well, you don't want the electrodes that they move around. You want the electrodes to stay in those well-defined positions that you're interested to take the recording of. You're probably going to use glue, or you're going to use caps. One word of wisdom. Electrophysiologist and neuroscientist likes to use caps for EEG recording. That's the most wrong way to record EEG ever. Why? I challenge you to do 2 recordings of the same participant with the cap placed exactly in the same position all the time. That is not possible. Also, caps, they are in a kind of either one size fit all or in 2-3 sizes. You have like a small, medium, large. I've seen heads coming in all shape and sizes. Also, caps, they might not take into account the fact that somebody might have a head that is much more developed in one direction rather than another direction. The only way to make sure that you record EEG from always the same position, I'm afraid, is the long preparation of the head, which takes up to 3 minutes per electrode, because you need to apply your individual electrodes. How do you use cap without worrying too much? There is a way of doing it. Using the overkill principle, which means 250 electrodes. If you have a very dense cap and you are interested into specific part of the cortex, using a very dense cap and modeling the head as a sphere all the time, then you just do focuses of activation, so you group electrodes around specific results of experiments. Then as soon that you don't try to go into the details and say, oh, but why this area with those boundaries today is active while yesterday was this area was a bit shifted on this side. As soon as you don't try to do that, the cap is fine. But exactly in the moment that you try to claim position into the head and of the sources into the head using EEG with a cap, then neurophysiologists, engineers, and other people are going to point the finger at you and say you're going to do it wrong. Okay, so this is just a word of wisdom. Preparing a subject or a participant, as people like to call the people that volunteer for the experiments, it is a long process. And if it's not done properly, it's going to mess up your experiments. And this slide, this picture, should clarify briefly why that is so important. Everybody thinks, okay, I'm going to record ECG, I just stick electrodes. If you don't prepare well the skin, well, you're going to create a bunch of other impedances in between the electrode, the body, and so the amplifier. They're going to cause noise. Same is for the cap on the EEG. If you don't take care, there are some cap for EEG, I've seen them, where you actually, what you do, you actually pull the air out of the electrode so that you can actually use the hair of the participant to create a wet column of gel to make sure that you touch the scalp. There's nothing worse for EEG to have a mat of hair in between your electrode and the scalp. Why? Well, you fill the electrodes with electrolytic gel or glue. If there is a mat of hair squashed between the scalp and the electrode, what the gel does is going to smear. And when it smears, if you have nearby electrodes, guess what is going to happen? You're going to short electrodes out. And this is one of the major causes of boundary alteration into the brain activation maps done with EEG signals. Every time people, when I'm asked to review paper done in this way, I ask how dense was the cap and what were the precautions against electrodes gel smearing. Because if you don't take this into account, or you don't check, so there are caps that actually use a kind of a solidified gel, and when you remove the cap, you can actually see if there is a bridge in between electrodes. So preparation of your participant and goes hand in hand with assessing of the data. And most importantly, you might want to look at what happened, for example, when the participant removed the cap. Or when you do go and remove the electrodes, is the skin under the electrodes red? Is there something that was happening to the skin because of the electrodes or my gel? does this cause noise onto the recording? All these factors, if you don't take them into account, you make this model more and more complicated. And if you don't know, then your data might be not worthwhile your time and the participant time. Well, we discussed about this kind of. You probably are aware that every time a metal is in contact with a non-neutral solution, there is some redox reaction at the interface. That's what is going to happen. In order to make the redox known, the skin has to be prepared. If and this is often the case of when you do like ECG recording, or even EEG, because EEG. EEG recording, sometimes you record electrodes from the frontal cortex. Well, what happens if in the morning you used some soap to wash your face and you haven't rinsed it properly? The soap is going to change slightly the pH of the skin. That means that the electrodes that they go on the frontal area, they're going to face a different redox reaction of the one that they go in between the hair. Hang on, the hair, they could be dirty. Or you might have used some product to keep your hair dough, like those gels or pastes that they keep the hair in position, or sprays. All those things, they could actually change the pH of the hair and change the pH of the scalp. Although this might sound terrible, but in the lab where I was before, all the participants were asked to rinse their hair, even ladies, with saline solution. Clean completely the hair with purified water and saline solution, and then dry the hair. I know that if you actually start doing that, the number of your volunteer participants might drop down a lot. But it all depends on what you're doing. So there are some electrodes material that you see all the time. Have you ever asked yourself why they are always the same? The reason why they are always the same is in this table. What do we want from an electrode that either act as a very low value resistor or that act as a very high value resistor, namely a capacitor? In other words, what we want an electrode that is either totally polarizable or totally non-polarizable. So gold and aluminium, they sit into the non-polarizable band of the spectrum. Silver chloride, and something that we can't use, which is mercurium, they do the other way around. So if you look at that, they actually, one has a very low alpha cell potential and one has a very high alpha cell potential. So mostly silver chloride and gold are used for external electrodes. If for internal electrodes, normally what you do, you probably use a silver wire or a platinum wire, or sometimes it's just a pipette, glass pipette or metal pipette filled with saline solution. So you use the saline solution as electrode. We discussed about this. This is another issue that a lot of electrophysiologists, they just don't take into account. according to the frequency of interest and according to the frequency of stimulation sometimes, we need to change the kind of electrodes that we use. That is because electrodes, they have a kind of a characteristics with the frequency. So they have a proper frequency response. So their impedance changes according to the frequency of stimulation or the frequency of the signal that we're interested. I often joke with my students, which are engineers, that they should take that figure, this one up here, print it, laminate, and keep it in their wallet aside their beloved ones. That is because it tells you that every signal has a different response with the frequency, well, different frequency content in terms of amplitude and frequency axis, but also some, they are much more influenced by the choice of the electrode. So for example, electrode potential are in this dark gray region, and you see that they actually they have value, that they are larger than every physiology signal because they sit up here in the voltage scale. And in terms of frequency, well, if I'm doing some electromyogram from the muscles, probably I will not care about my choice of electrode. And that is because that's the reason why sometimes electromyogram electrodes, they're just like rubbery patches with or without gel, or sometimes stainless steel needles. That is because those signals, they sit so up high into the frequency that we don't really care of what is the frequency, behavior, or impedance of the electrode. Different is if you're doing EEG. EEG sits into the frequency range that is almost completely covered by the electrode's potential. And in terms of amplitude, because the EEG really stops down here into fraction of millivolt, you see that the electrode potential, they have a value that can completely obliterate or cancel your signal. How these electrodes, artifacts, if you like, cancel your signal? Easy. If I want to amplify a signal that is a fraction of millivolt, in order to make it visible, I need to transform this signal into a fraction of a volt. So I need to amplify at least 1,000 times. However, the same amplifier is amplifying 1,000 times, not just my signal, also the noise. If I'm amplifying 1,000 times something that is already volts or fraction of a volt, this become thousands of volts or hundreds of volts. Well, I got an issue here that I can't represent simultaneously this large dynamic range. That's the main issue. So guess what is going to happen? Guess what you're going to see on your recorder? Fantastic flat traces. But we'll discuss about this in detail. One other issue is the motion artifacts that affect the electrodes and in general all the interfaces with volume conductors. Motion artifacts, they mostly affect you for in vivo recordings. If you're doing some ex vivo or excised cells or brain slices or whatever recording, the only motion artifact is the actual motion of the building. And as Yossi told you about his nightmare when they were building another building on Campbell Down campus. Well, what was happening, although the construction work was, I think, 1.5 km away, the vibration into the soil inflicted by the machine that was actually hammering down the pillars of the new building. They were transmitted to his lab, and although he uses an anti-vibration table, he was observing displacement of micrometers under the microscope. If your cells are floating into a saline solution bath and you shake it, what is going to happen? They're going to move. If you trust a pipette to keep a stable bridge between the recording machine and to the cellular membrane you're probing, and the cell moves, guess what is going to happen? All of this network is going to generate something, new voltage, new current. So your recording is simply impossible. Example in vivo, you're recording EEG and your volunteer sneezes or cough or move the head or blinks. Try to put a finger on the top of your head and blink, or actually on your forehead and blink. You should be able to feel the movement under your finger pads of the skin. So, believe it or not, from the EEG recorder, the blink can be seen even from electrodes at the back of the head. My experience with EEG recording, one day I was really going crazy. I needed to record EEG from very well specified electrodes, only those electrodes and nothing else. So I had the subject perfectly prepared, the electrodes position measured, everything. I had a fantastic ECG artifact under one of the recording electrodes. And this was because that specific volunteer had a small arteria going under the skin of his scalp, right under the electrode. That was making the electrodes to bump away from the skin of, well, obviously not something you can actually observe, but that was happening, and I had this bumping EEG. That was exactly in rhythm with the heart. How do you solve these kind of things? Well, luckily for me, I was with an expert doctor that saw the data, went and told to the participant, relax, grabbed his head and the pillow, and moved his head in a very awkward position using a pillow. And the guy was looking at me like this. He said, "Oh no, stay like this," and the artifact disappeared. That is because changing the feeding angle of the small arteria reduced the bumping. But in order to know how these things, you need to do a lot of recording and you need to understand what's happening. Anyway, so those are the most common kind of electrodes that you're probably going to use. Some of them, they are rubbery electrodes, like this one, mostly used for stimulation. Skin electrodes for EMG, ECG, they mostly present like cups, where you actually, the metal disc doesn't touch the skin directly, but there is a sponge filled with some electroconductive gel or paste, or you actually fill it by yourself before performing the recording. And that's the case sometimes of EEG cups, that they look like really a little cup with a hole at the top sometimes. And you just fill it with paste and you stick them in position. Or if they are into a cup, the hole on the top is used for you to fill with conductive paste or gel. Obviously, if you do some probing, particularly of cells, you might gonna use needles and pipette electrodes. Pipette and needles electrodes, they could be either glass or metal. Doesn't really matter which kind of they are. They all have an equivalent circuit that, and this might come as a surprise for some electrophysiologists. Every time I discuss this with electrophysiologists, they believe that pipette electrodes, they are perfect, or they are easier because you actually break the skin or the membrane barrier. Actually, the electrical model of pipette electrodes or needle electrodes could be more complicated than surface electrodes, particularly in the cases where you actually have a reference or a neutral electrode placed somewhere else that is not a pipette. And that's sometimes the case when you actually have a large bath with cells and pieces of nerve or slices, brain slices, and you probe them and you use the bath itself as a reference electrode. Well, as you can see over here, the electrical circuits model, they are pretty complicated. So this is to say, take care of preparing the recording. Make sure of the pH of your solution. Make sure that the electrodes or needle or pipette is in the right position. Make sure that if a bridge is to be formed between the tip of the pipette and the intracellular space or the membrane of the cell is the right one. Don't overlook this thing because although your signal might look right, so you might be very lucky, is this right? The experiment might be flawed because you don't know what's happening in between all these capacitors, all of this the resistive network, if your electrodes are not prepared well. So please don't do like the typical neurophysiologists just say, oh, if I break the skin barrier, I'm fine. No, you're not. And your participant will appreciate if you're breaking the skin barrier with needles, that you're doing it properly and you're doing it only once. So electrodes for stimulation, they are extremely important. If you don't prepare well the patient or the subject or participant's skin for stimulation, you're going to inflict severe damages. I'm not joking, you can actually give them second or third degree burns. So what is the principle of functioning of a hair dryer or a stove? You make a current to circulate into a very large, thick resistor, which is going to heat up by thermal effect. This is going to happen at the interface between the electrodes and the skin if the resistance, the contact resistance or impedance is very high. And in case of recording, if this impedance is high, you destroy your signal, you don't see any signal, and then you curse yourself because you could have prepared the skin better. In case of a stimulation, if you don't see the effect, which could be like twitching, you're stimulating nerves to see the twitching into hands or feet or whatever, and you don't see the effect, what are you going to do? The very first thing everybody does goes and crank up the dial of the stimulation current. That is the most possible wrong way of acting. Because if there is a large contact impedance, there is a large resistor, if you make a large current to circulate into a large resistor, you're going to create a little stove under the electrodes, which could cause a burn, blisters and burn, up to second or third-degree burns. I'm not joking. So obviously there are different waveform